तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
In the last lecture, we saw about the pigeonhole principle. Today, we shall see permutations and combinations. What do we mean by combination? It is the ways of selecting some objects out of some objects. Suppose you are having n objects, you want to select r objects out of it. It is a selection. This is called combination. And the number of ways of arranging r objects out of n objects, that is called arrangement or permutation, and we shall see some formulae, and we shall also work out a few examples regarding this. Generally, the notation CNR, it represents the number of r combinations of n distinct objects, and the notation PNR, it denotes, PNR denotes the number of r permutations of n objects. That is CNR, this is the number of ways of selecting r objects out of n objects. Sometimes it is also denoted as NCR. Similarly, PNR, and this is also denoted as NPR sometimes, and sometimes in some notation they also represent like this, NPR. These are other notations. Permutation, number of permutations of r objects out of n objects. That is, you are having n object and you are taking r of them and arranging them. That is the number of permutations of r objects out of n objects. Number of selecting r objects out of n objects is known as the combination, and it is denoted by CNR. Other notations are given here. Generally, we have two rules. One is the rule of product and another is the rule of sum to attack problems based on permutations and combinations. The rule of product says that if one event can occur in m ways and another event can occur in n ways, then there are m into n ways in which these two events can occur. This is known as the rule of product. We will be using both the rules frequently. The rule of sum says if one event can occur in m ways and another event can occur in n ways, there are m plus n ways in which one of these two events can occur. So, we will mention when we make use of these rules. Let us take a simple problem and see how we tackle the problem. The problem is, in how many ways can you choose 2 books of different languages among 5 books in Latin, 7 books in Greek and 10 books in French. So, you are having Latin, Greek, French. How many books do you have in Latin? 5 books in Latin, 7 books in Greek and 10 books in French. And you are asked to select 2 books of different languages among 5 books in Latin. So, you can choose this way, you can choose 1 book from Latin, 1 book from Greek, or you can choose one book from Latin, one book from French, or you can choose one book from Greek and one book from French. Suppose you choose from Latin and Greek, one book from this, one book from this. In how many ways can you choose a book from Latin? Out of the 5 books, you can choose one in 5 ways. And in Greek, out of the 7 books, you can choose one book in 7 ways. So 5 into 7, there are 35 ways of selecting one book in Latin and one book in Greek. This is the rule of product you are making use of. Then in how many ways can you choose a book from Latin and one book from French? One book from Latin and one book from French. You can choose one book from Latin in 5 ways, and you can choose one book from the set of French books in 10 different ways. So totally in 50 different ways you can select a book from Latin and a book in French. Again you are making use of the rule of product. Now suppose you are choosing a book in Greek and you are choosing a book in French. In how many ways can you choose a book in Greek? You can choose a book in Greek in 7 different ways, and you can choose a book in French in 10 different ways. So in 70 different ways you can choose a book from Greek and a book from French. So we are making use of the rule of product. Now we will make use of the rule of sum. So you can either choose a book from Latin and Greek, a book from Greek, a book from Latin and a book from French, or a book from Greek and a book from French. So in how many ways can you choose 2 books of from different languages? That means you have to add this is the rule of sum. So you will get 5, 155. In 155 different ways you can select 2 books of different languages among 5 books in Latin, 7 books in Greek and 10 books in French. So we have seen how to make use of the rule of product and rule of sum. Now what is the value of PNR and CNR? By the rule of product, PNR is equal to PRR into CNR. What do you mean by this? PNR is the number of R combination of R objects out of N objects, and that is equivalent to CNR into PRR. It amounts to saying that this left hand side represents the number of ways of selecting R objects out of N objects and arranging them. So now this is the number of permutations of R objects out of N objects, and this is equivalent to saying that you select R objects out of N objects, and after selecting you arrange them, that is PRR. So you can represent in this way. Now by the rule of sum you will get this CNR is equal to Cn minus 1 R minus 1 plus Cn minus 1 R. How do you get this? CNR is the number of ways of selecting R objects out of N objects. Now among the N objects you mark a particular objects. You can, there are 2 possibilities. You can select this object or not select this object. Suppose you select this object. There are 2 possibilities, select or not select. If you select, then from the remaining n minus 1 objects you have to choose R minus 1 objects. That is equivalent to saying C n minus 1 R minus 1. If you do not select this object, from the remaining R minus 1 objects n minus 1 objects, you have to select R objects, and that is C n minus 1 R. So, you get this, and obviously you are applying the rule of sum here. Let us see what is the value of PNR, that is the number of R permutations out of n objects. It is equal to n factorial by n minus R factorial. This is the formula for PNR. Let us see how to derive it. We are having n objects, and you are asked to arrange R of them in R places. R places. Now, how will you arrange? So, the first place you can pick one of the n objects and put it here. That can be done in n ways. Then after selecting one object and putting it here, you will be left with n minus 1 objects here. So, the second place you can fill in n minus 1 ways. So, the first place you can fill in n different ways, and after doing that, the second place you can fill in n minus 1 ways. So, the first two places can be filled in n into n minus 1 ways. So, after filling the first two places, you will be left with n minus 2 objects here. Pick one of them and put it in the third place, and that can be done in n minus 2 ways. And similarly proceeding, the rth place can be filled in n minus r plus 1 ways after selecting r minus 1. After filling the r minus 1 places, the rth place can be filled by selecting one object out of the n minus r plus 1 objects. So, this is the number of ways, this into this into this into this, the number of ways we can arrange r objects from n objects. So, PNR is equal to this, and this is nothing but n into n minus r plus 1. You can multiply by n minus r minus 1 up to 1, and below also the same number n minus r into n minus r minus 1 and so on. So, this the numerator is n factorial, the denominator is n minus r factorial. So, PNR is equal to n factorial by n minus r factorial. You can also derive it in a slightly different manner, that is like this. First of all, you prove that PNN is n factorial. The number of ways of arranging n objects is n factorial. How do you, this you can prove by induction. First of all, P11 is 1 factorial, obviously, that is true, and suppose P n minus 1 comma n minus 1 is n minus 1 factorial by induction. This is the basis class of the induction, this is the induction class. Then from this, how do you prove n minus np and n is n factorial? After arranging n minus 1 objects, you are having n objects, n minus 1 of them you have arranged in n minus 1 factorial ways. Then the last object you can put here and so on in n ways. So, P n n is P n minus 1 n minus 1 into n, and by induction this is n minus 1 factorial into n. So, this is equal to n factorial. So, by induction we can prove that the number of ways of arranging n objects is n factorial. Having proved this, how do you get PNR is equal to n factorial by n minus r factorial? Now, PNR is the number of ways of arranging R objects out of n objects. Now, suppose I have n objects and I want to arrange PNN. This I can do by filling arranging them in n places, okay, n places. First I can take R places and fill them, then the remaining n minus R places I can arrange, okay. So, PNN is equal to, first I pick R objects out of n objects and arrange them, that is PNR. Then the remaining PNR, and then the remaining n minus R objects can be arranged in the n minus R places, and that is Pn minus R comma n minus R. And we know that this is n factorial, and PNR is this. Pn minus R is n minus R factorial. So, from this also you get PNR is equal to n factorial by n minus R factorial. So, let us see. Of course, we have seen that PNN is n factorial. So, we can make use of this in solving problems, but instead of having a linear array, you want to arrange n objects as a linear array, and that is why we have first place we filled in n ways, then the second place in n minus 1 ways, and so on. Suppose instead of having a linear array, you want to arrange n objects in a circular manner. N objects you have to arrange along a circle 1, 2 to n. In this case, suppose I have one arrangement A1, A2, AN, A1, A2, AN, and another arrangement AN, A1, A2, AN minus 1. When you look at it as a linear array, suppose you are having chairs, say, you are having 5 people seated in 5 chairs, say. The 5 people's name may be A, B, C, D, E, say. So, you can arrange them something like this, A, B, C, D, E. This can be done in 5 factorial ways. We know that this can be done in 5 factorial ways. But when you arrange them in a circle like this, 5 chairs are arranged in the form of a circle, A, B, C, D, E. Then the arrangement A, B, C, D, E and E, A, B, C, D are the same as far as the circular arrangement is concerned. But when you consider it as a linear arrangement, they are different. Okay? So, A, B, C, D, E, E, A, B, C, D, D, E, A, B, C, C, D, E, A, B, B, C, D, E, A, all are same. So, in a circular arrangement, one arrangement corresponds to, say here in this example, 5 arrangements in a linear manner. So, like that, if you have n objects, one arrangement here will correspond to n arrangements when you look at it as a linear circular, and this is linear. So, one arrangement here will correspond to n arrangement, and the number of linear arrangement is n factorial, this we know. So, the number of circular arrangements will be equal to, each one corresponds to n. So, this divided by n gives the number of circular arrangements, and that is equal to n minus 1 factorial. So, the number of ways in which n people can be arranged in a circular way, or n objects can be arranged in a circular way, is given by n minus 1 factorial. Let us consider some more results. Here whenever I said arranging n objects, arranging R objects, the objects are considered to be distinct objects. So, so far we have been considering arranging of distinct objects. PNR denotes the number of ways of arranging R objects out of n distinct objects. The objects are not the same. Suppose the objects are not distinct, they are, some of them are similar or same, then how do you calculate? For example, you may have red balls and blue balls, then how do you arrange them? See, whether I have two red balls R1 and R2, they are identical, and I have blue balls, two blue balls B1 and B2. Then R1, R2, B1, B2 is different from R2, R1, B1, B2 if you look at them as distinct objects. But when these two red balls are identical, these two arrangement are the same, red, red, blue, blue, that is what you are going to get. So, in such a case, what is the formula for arranging n objects? So, now we have n objects, but they are all not distinct. Let there be n objects that are not all distinct. Specifically, there are q1 objects of the first kind, q2 objects of the second kind, and qt objects of the tth kind. Then the number of n permutations of these n objects is given by the formula n factorial by q1 factorial, q2 factorial, qt factorial. So, you are having n objects, not all of them are distinct, q1 objects are of the first kind, q2 objects are of the second kind, and so on, and qt objects are of the tth kind. In how many ways can you arrange them? If they are all distinct, the answer is n factorial, that we know, but some of them are similar. So, the answer will be much less, it will be less than n factorial. Let us see what it is. Suppose I have, say, q1, a1, a1, a q1, these are the objects of the first kind, q1 objects. If I mark them distinct, then I get different objects, distinct objects. Similarly, say the second objects, I call them as B1, B2, BQ2, make them all distinct, and so on. If I do this, all objects become distinct. Okay? So, the number of ways of arranging them is n factorial, this we know. But since a1, a2, aq1, they are all not distinct here, they are all same, they are objects of the same type, say like red balls, blue balls, what I considered earlier. So, if you consider them as same object, then you see that if you take one permutation here, and then in that one permutation or one arrangement here, and within that this first objects you can arrange in any manner you want. See, all this a1, a2, aq1 or a2, another arrangement, they will all correspond to the same arrangement when we look at them as the same non-distinct objects. So, if you take a particular permutation, and within that particular permutation you consider only the objects of the first kind. One such arrangement, when you look at them as non-distinct, will give rise to q1 factorial times the number of arrangements when you look at them as distinct. So, when you look at it as non-distinct, you have to divide by q1 factorial. This is with respect to the first kind of object. Then the similar thing holds for second kind of object. Look at the second kind of objects. The permutation here, when you look at them as distinct objects, when you look at them as non-distinct objects, will give rise to q2 factorial times the number of arrangements when you look at them as distinct objects. So, one permutation give rise to q2 factorial permutations when you look at them as distinct objects. So, when we look at them as non-distinct objects, we have to divide this n factorial by q2 factorial and so on. So, similarly qt factorial. So, the number of ways of arranging n objects when the objects are all not distinct and where q1 of them are of the first kind, q2 of them are of the second kind and qt of them are of the tth kind is given by n factorial by q1 factorial, q2 factorial and qt factorial. This is the formula. So, this is given by this. Okay. Let us do a problem under this. In how many ways 5 dashes and 8 dots can be arranged? You are having the telegraphic code earlier, we used to have dashes and dots. There are 5 dashes and 8 dots, right? In how many ways can you arrange them? Totally you have 13 factorial, but you cannot distinct between, you cannot make a distinction between the between the dashes and the dots. So, that will be 5 factorial, right? And total number of ways of arranging 5 dashes and 8 dots is this. Suppose I want to arrange only 7 of them, 7 of them. I do not want all, this is the arranging all the 13, right. Now, I want to arrange only 7 of them, pick up 7 of them and arrange them. In how many ways can you arrange 7 dashes and dots, picking them from 5 dashes and 8 dots. Now, dashes and dots, there are at the most 5 dashes. So, you can select 5 dashes and 2 dots for 7, or you can choose 4 dashes and 3 dots, or you can choose 3 dashes and 4 dots, or 2 dashes and 5 dots, or 1 dash and 6 dots, or you can select all the 7. So, for each one, what will be the formula? If you select, if you take 2 and dots and 5, this will be 7 factorial by 5 factorial into 2 factorial. If you select 4 and 3, that will be 7 factorial by 4 factorial into 3 factorial. If you select 3 and 4, it will be again 7 factorial by 3 factorial by 4 factorial. And if you select 2 and 5, it will be again 7 factorial by 2 factorial 5 factorial, plus you select this we have 1 and 6, it will be 7 factorial by 1 factorial and 6 factorial. This is plus 7 factorial by 0 factorial and 7 factorial. 0 factorial is taken as 1. Okay. So, this you have to sum up this. Let us take one more problem. This is about numbers, but using combinatorial arguments, how do you prove this? Show that k factorial factorial is divisible by k factorial to the power of k minus 1 factorial. The problem is to show that k factorial is divisible by k factorial to the power of k minus 1 factorial. How do you prove this? Using combinatorial arguments. Suppose you have k factorial objects. You are having k factorial objects. Actually, that is equivalent to saying you are having k minus 1 factorial into k objects. And suppose they are not distinct. There are k objects of first kind, there are k objects of second kind, there are k objects of third kind, and so on. Like that, there are k objects of k minus 1 factorial kind. So, out of the k factorial objects, k of them are identical of the first kind, and k of them are identical and are of the second kind, k of them are identical of the third kind, and so on. So, in what is the number of ways of arranging them? The number of ways of arranging k factorial objects is given by k factorial by capital. If they are distinct, the number of ways of arranging k factorial objects is given by this formula. But we know that k of them are of one kind, k of them of the second kind, and so on. So, using the formula which we derived earlier, you have k factorial because first kind objects are of k type, then second kind objects are, there are k objects of the second type, there are k objects of the third type, and so on. Like that, you have this number is k minus 1 factorial times. So, you are dividing this by k minus 1 factorial 10. So, this is equivalent to saying k factorial by k factorial to the power of k minus 1 factorial. And what is this? This is the number of ways of arranging k factorial objects, of which k of them are of the first kind, k of them of the second kind, and k of them are of the k minus 1 factorial kind. And this is something, it should be an integer, it cannot be a fraction or something, it has to be an integer. And so, this is an integer, which would mean that this number is divisible by this number. Okay. So, by a combinatorial argument, you are proving that this number is divisible by this k factorial is divisible by k factorial to the power of k minus 1 factorial. Now, let us consider combinations or the number of selections. CNR is given by this formula. CNR equal to PNR by R factorial equal to n factorial by R factorial into n minus R factorial. How do we get this? See, CNR is the number of ways of selecting R objects out of n objects. And what is PNR? PNR is the number of ways of arranging R objects out of n objects. So, you get this. When you want to get PNR, you have this. First, you select R objects out of n objects, that is CNR, then arrange them, that is PRR, that is given by CNR into R factorial. And PNR we know is n factorial by n minus R factorial. From this we derive CNR is equal to n factorial by R factorial into n minus R factorial. So, we have derived the formula CNR is equal to n factorial by n minus R factorial into R factorial. And we also see that CNR is equal to Cn n minus R. This straight away from the formula we can derive, or you can also give it a combinatorial explanation. What is CNR? CNR is the number of ways of selecting R objects out of n objects. It is also equivalent to saying that you are rejecting n minus R objects, you are not selecting n minus R objects. So, the number of ways of rejecting n minus R objects is or you are choosing n minus r objects and rejecting them, that is given by Cn comma n minus r. So, the number of ways of selecting r objects out of n objects is the same as the number of ways of rejecting n objects out of n objects, and so Cnr is equal to Cn n minus r, and this is also derivable from the formula. Let us take an example. If no three diagonals of a convex decagon meet at the same point inside a decagon, in how many line segments are the diagonals divided by their intersections? Because simple problems we can consider in how many ways can you select 2 books out of 5 books is 5C 2 ways and so on, C5 2 ways and so on. Those things are simple. Let us take a slightly more involved problem. So, this is the problem we are considering. If no three diagonals of a convex decagon meet at the same point inside the decagon, in how many line segments are the diagonals divided by their intersections? How do you argue it out? So, you are having a convex decagon, that is 10 sides and 10 vertices, of course. How many diagonals it will have? A diagonal is obtained by selecting 2 vertices out of n vertices, 10 here. Okay. So, the number of ways of selecting 2 vertices out of 10 vertices, number of ways of selecting 2 vertices out of 10 vertices is given by C 10 comma 2 is 10 factorial by 2 factorial into 8 factorial, that is 10 into 9 by 2 equal to 45. But out of this 45 line, each line segment joins 2 vertices. Out of the 45, 10 are sides. We want only the diagonals, we do not want the sides. There are 10 sides. So, diagonals, number of diagonals is 45 minus 10, 35. Now, how many intersecting points you can have? If you choose 4 points, then there will be a intersecting point corresponding to the 4 vertices. If you choose any 4, you will get a intersecting point. And it is said that all the intersecting points are all distinct. So, how many intersecting points you will get? Number of intersections. Number of intersection is given by C, number of ways of selecting 4 vertices out of 10 vertices, and that is given 10 factorial into 4 factorial into 6 factorial, and that is equal to 10 into 9 into 8 into 7 by 1 into 2 into 3 into 4 equal to 210. So, the number of intersection is 210, and look at, let us just consider 2 diagonals, and one intersection will, this is one diagonal, this suppose there are 2 intersections, something like this on this line, this is a diagonal, there are 2 intersections. Initially you had only one. This intersection has added this line segment, this intersection has added this line segment. So, each intersection adds one line segment for our calculation, and this intersection is on 2 diagonals. So, it will add one line segment in one diagonal and another line segment in another diagonal. So, each intersection will add to 2 line segments. So, if you look at it, the question is how many line segments are the diagonals divided by their intersection. Initially there are 35 diagonals, and each intersecting point adds a line segment, and it adds a line segment in 2 diagonals. So, and the number of intersecting points is 210. So, that is 2 into 210 times, and that will give you 35 plus 420 equal to 455. So, in a convex decagon, if you assume that the diagonals, no 3 diagonals of the convex decagon meet at the same point, that is the intersecting point of the diagonals are all distinct. In that case, the number of line segments into which the diagonals will be divided is given by the number 455, and you get this by arguing out this way. The next we will consider one more method. When repetitions in the selection of the objects are allowed, what is the number of ways of selecting R objects from n objects, n distinct objects? Of course, we are not considering non-distinct objects, we are considering distinct objects. When repetitions in the selection of the objects are allowed, the number of ways of selecting R objects from n distinct objects is given by C n plus R minus 1 comma R. How do you get this? So, n distinct objects are there, and you are allowing repetition. Instead of looking at as n distinct objects, you look at them as numbers 1 to 3 to n numbers, and I want to select R numbers where repetitions are allowed. For example, 2 I can select 2 times, 5 I can select 3 times, 7 I can select once, 8 I can select 2 times, and so on. That I can select. I want to select R of them out of n. Repetitions are allowed. Now, in this case, I select and write them like this: I, I1, I2, I3, that IR. Here some of the i's may be the same, then they are not distinct, repetitions are allowed, but I am arranging them in the increasing order. They are arranged in the increasing order like this, like 2, 5, 7, 8, like that. Now, I add 0 to I1, 1 to I2, 2 to I3, and so on, and R minus 1 to I. So, to I1 I add 0, to I2 add 1, to I3 I add 2, and so on. To IR I add R minus 1. Again, they are all numbers, but they are all distinct numbers, they are not the same. So, this way you are selecting R distinct integers. Now, the integers are not from 1 to n, but they can be up to n plus R minus 1, because if you add R minus 1 to n, you will get n plus R minus 1. So, this is equivalent to saying that you are selecting R distinct objects I1, I2 plus 1, I3 plus 2. You are selecting the integers I1, I2 plus 1, I3 plus 2, IR plus R minus 1. They are distinct integers from the set 1, 2, 3 up to n plus R minus 1. This is equivalent to the number of ways of selecting R objects out of n plus R minus 1 distinct objects. And so, that is given by C into C n plus R minus 1 comma. Like that we get this result. So, when repetitions in the selection of the objects are allowed, the number of ways of selecting R objects from n distinct objects is given by Cn plus R minus 1 R. Let us consider a simple problem here. You are having 1 rupee coins, 2 rupees coins and 5 rupee coins. You want to select 6 of them. Select 6 of them. From a collection of 1 rupee coins, 2 rupee coins and 5 rupee coins, you want to select 6. In how many ways can you? How many ways? The answer is there are three types and you have to select 6 of them by repetition. You can use repetition. So, the answer using the formula is C 3 plus 6 minus 1 comma 6. This is the answer is this. What is this? C 8 comma 6 and that is given by 8 factorial by 2 factorial into 6 factorial, which is 8 into 7 by 2 equal to 28. This is the answer. And if you want to, if you have some doubt about it, let us check. How do you get this 28? So, you have 1 rupee coins, 2 rupee coins and 5 rupees. You can select all of them to be 1 rupee coins. You have to select 6 coins. So, you can select all of them to be 6 or all of them to be 2 rupees coins and all of them to be 5 rupee coin. That can be done in 3 different ways. If you select 5 of them as 1 rupee coin, the second one you can choose as a the sixth one you can choose as a 2 rupee coin or you can choose as a 5 rupee coin. Similarly, if you choose 5 here, you can choose 1 here or you can choose 1 here. If you choose 5 here, you can choose 1 here or you can choose 1 here, and this way this accounts to 6 possible ways. And if you select 4 of them and again 2 of them from this or 2 of them from this, like that you can select 4 from here, 2 from this and 2 from this. That again can be done in 6 ways. You can select 4 of them from one kind and 1 from the other 2 kind. That will give rise to 3 different ways. And if you select 3 of them of one kind and 2 of them from the one and 1 from the other one, and this can be done in T, that is you can have 3 to 1 or 3 to 1 like that, and this way you can select in 6 possible ways. And you can select 2 to 2, that is in one way, or you can select 3 3 from 2. You can select 3 3 here, or you can select 3 3 here, or you can select 3 3 here, and that is again 6. So, add up and see. 1 2 3 4. That is, this is 3, I am sorry, this is 3. So, this gives rise to 3, 1 2 3, 18, 18, 24, 27, 28. So, you get this answer 28. Now, another example is this: when 3 distinct dice are rolled, the number of outcomes is 6 into 6 into 6, 216. So, you are having 3 distinct dice and the number of ways you can have the possible outcomes is First one it can show any one of the 6 numbers, second one it can show any one of the 6 numbers and so on. So, you have totally 6 into 6, 216 ways. If the 3 dice are indistinguishable, that is you do not want to distinguish between the first, second and third one, then the number of outcomes you have to use the formula C. So, there are 3 dice and 6 outcomes. So, it will be given by C 6 plus 3 minus 1 comma 3, which is 56. This is can be seen by considering the selection of 3 numbers from the 6 numbers when repetitions are allowed. So, you have to look at it this way and give the answer. So, the first one getting 216 is easy, but getting this number you have to look at this in this manner. You are selecting the 3 numbers from the 6 numbers where repetitions are allowed. You have to look at it to get the answer. Another problem is when the objects are not all distinct, the number of ways to select one or more objects from them is equal to q1 plus 1 into q2 plus 1 into qt plus 1 minus 1, where there are q1 objects of the first kind, q2 objects of the second kind and qt objects of the tth kind. There are q1 objects of the first kind. So, the number of possibilities is you can select one of them, you can select 2 of them, you can select 3 of them, you can select q of them, you need not select any one of them. So, the number of possibilities is given by q1 plus 1, and there are q2 objects of the second kind. So, you can choose 1 of them, 2 of them, 3 of them, q2 of them or not select any of them, that is given by q2 plus 1. Similarly, proceeding you get qt plus 1, the number of ways of selecting one or more objects of the tth kind or not selecting any of them. But the possibility, the question is the number of ways to select one or more objects. So, not selecting any of them, that possibility should be subtracted, that is why that minus 1 is there. So, the number of ways of selecting 0 or more objects of the first kind is given by q1 plus 1. The number of ways of selecting 0 or more objects of the second kind is given by this. The number of ways of selecting 0 or more objects of the tth kind is given by that. So, the number of ways of selecting 0 or more objects is given by this, but the number of ways of selecting 0 objects is not allowed. So, that is minus 1. So, this is formula gives you the number of ways of selecting the number of ways to select one or more objects from them when q1 are of them are of this first kind and so on. So, making use of this we can solve some problems. How many devices does the number 1400 have? So, 1400 we can write as 14 into 100 equal to 7 into 2 into 20 into 5 equal to 7 into 2 into 5 into 4 into 5 equal to 7 into 5 to 2 into 2 into 5, that is equal to 2 cubed into 5 squared into 7. A divisor of the number is obtained by selecting some or 0 of them or all of them, again some or 0 or all of them, and by selecting 7 or not selecting 7. So, the total number of possibilities is you can select 1 2 or 2 2s or 3 2s or no 2s at all. So, that is given by 3 plus 1 ways. So, in the earlier formula if you look at it, it is given by this q1 plus 1. And similarly, if you can select 2 5s, 1 5 or no 5s. So, that is given by 2 plus 1, and you can select 7 or not select, that is 2 possibilities, that is 4 into 3 into 2, 24 ways. But Please remember here that if we select all of them we get 1400, and we do not select any of them we get 1. So, 1 and 1400, if you look at them also as divisors, then the number of divisors of 1400 is given by this. So, here we are taking 1 and 1400 also as divisors. So, we have considered some problems based on permutation and combinations. The main thing is each problem we have to consider in a different manner, and there are some formulae. The main formula is PNR is n factorial by n minus r factorial, and CNR is n factorial by r factorial into n minus r factorial. And by looking at the problem, we have to decide which form, whether there are repetitions, there are no repetition, whether they are distinct objects or non-distinct objects and things like that, and then apply the corresponding formula and argue it out. So, we shall consider some more of combinations and permutation by distribution of distinct objects, non-distinct object into distinct cells and non-distinct cells in the next lecture.